Hello, geometry. Welcome to lesson 7 on similarity transformations. So in the last lesson, we talked about dilations, right? That's one of the transformations. So now we're going to talk about similarity transformations, building up our way towards similarity and how we show two triangles are similar. Okay, that's the section 7.3, I believe. So again, when you talk about similarity transformations, the only similarity transformation we know is a dilation. And again, you learned that last class. And dilations, the notation is a capital D with an N for the scale factor. Now, this is not to say that you cannot combine a dilation with a translation, with a reflection, with a rotation. But once you bring in a dilation, you are no longer a rigid transformation. You're a non-rigid. You're not going to be congruent. You're going to be similar. Okay. So let's take a look at this first problem here. It says if line M is represented by the equation x equals -3, what is a graph of the image of a reflection over line M composed with a dilation with a scale factor of 1/2 of triangle ABC? So remember that when you do these compositions, you must go right to left. So the first thing we're going to do is the dilation of a scale factor of 0.5. Now, because the center of dilation is not listed, it is the origin, right? So remember, the rule is when you do this to any point x, y, it's going to become 0.5 times x, so 1/2 of x, and 0.5 times y, 1/2 of y, right? So I'll just do that here. So A has coordinates of 2, 4. So when you multiply them by 1/2, you get coordinates of 1, 2. That's A prime. B has coordinates of -2, 8. So when you multiply by 1/2, B prime will be -1, 4. And C has coordinates of 0, 10. When you multiply them by 1/2, C prime is still at 0, but your 10 becomes a 5. And let's see this dilated version of our triangle. So 2, 4 becomes 1, 2. There's A prime. -1, 4 is B prime. And 0, 5 is C prime. And I call this like the intermittent triangle, or the middleman, right? Because what this did, it did the dilation, but it did not do the entire thing, because now we have a second step. And our second step is a reflection. And we are reflecting this new triangle over line M, which has the equation x equals -3. X equals, sorry, -3. What this means is y can be anything, but x must be -3. Go to where x is -3 right here. If y can be anything, that means that this line of reflection is a vertical line, up and down along when x is equal to -3. Sorry about the lack of straightness. So this is x equals -3. So remember, when you do a reflection, you just have to count, right? So A prime is 1, 2, 3, 4 way. So the true A prime is going to be 1, 2, 3, 4 way this way. There's A prime. You can call it A double prime if you want to. B is 1, 2 way, so B double prime would be 1, 2 way. There's B double prime. C prime is 1, 2, 3 away, so C double prime is 1, 2, 3 away. And there is going to be our final. That will be our final answer. This triangle dilated by a scale factor of 1/2 about the origin, and then reflected across this line, x equals -3. Okay, next. Okay, is there a composition of transformations that maps triangle XYZ to triangle JKL? Explain. Right? So if you take a look here, first of all, I notice that these two triangles are different sizes. And if they're different sizes, automatically I know that I have to use a dilation, potentially. Right? I automatically know that. So the other thing I notice is that if you look at these two triangles, to get triangle XYZ to become triangle JKL, I think I have to do a rotation, right? If you look at the orientation of them, I think you could also do a double reflection. You could reflect across the y-axis and the x-axis. I think that could work. But I'm going to do a rotation of 180 degrees because I want to get it from quadrant 1 into quadrant 3. So I'm going to rotate this guy 180 degrees, and that'll take me 2 quadrants counterclockwise. Okay. So now we're going to do this ourselves first. No, let's explore first. All right. So I'm going to pause it, open up Savas, and I'll bring it back to you. All right, so let's go explore this real fast. They do a good job of showing us how to do this. It's loading, loading, loading. I'm going to pause it while it's loading. All right, so I apologize. It's not loading. So we'll just go ahead and do this by ourselves. So what I was going to show you is going to show you the rotation and the dilation with this different scale factors on these sliders. So again, we talked about we got to rotate 180 degrees and dilate. Now, I like to dilate first. The reason I like to dilate first is because then it's going to give me better coordinates. So then maybe I can connect the rule with the coordinates for my rotation. So that's what I'm going to do first. It's actually reverse of what they did. They did the rotation first and then the dilation. Okay. So first thing I need to do is I need to find the scale factor, right? I need to compare a pair of corresponding sides. You need to pick a side that is horizontal or vertical. So it looks like XZ is the only side that is horizontal. Now, these blocks each are worth 2, right? 2, 4, 6, 8, 10. So from X to Z is the length of 2. So then that's going to compare, XZ compares to JL. JL is also horizontal. It's going to be a length of 4. So you can see that from XYZ to JKL, we doubled, right? To find the scale factor, you can do 4 divided by 2, right? The new length divided by the old length. But again, how do you get 2 to become 4? You multiply it by 2. So there's your scale factor, right? So we're going to do a dilation about the origin scale factor of 2. All right. So here comes our new, so I'll do it right down here. So X, which was at the point, again, counted by 2, is 2, 1, right? 2, and then halfway up would be 1, is going to become, if you double it, is going to become 4, 2. Y, which is at, again, 1, 4, again, counted by 2s, it will become y prime at 2, 8. And z, which is at 4, 1, will become z prime at 8, 2. And I'm going to graph that. So 4, so 2, 4, 2. There's x, not there. That's going to be in the middle of the triangle. So that is going to be my x prime. And then y is at 2, 8. So 2 and then 2, 4, 6, 8. There's my y prime. And then z is at 8. 2, 4, 6, 8, 2. And you can see what happened is we made our triangle bigger. Okay. And now what I would do is I would compare, right, x prime's coordinates, which are now at 4, 2, to j's coordinates, which are at -4, -2. And I'd say, oh, they made both become negative, right, or both opposite. That is precisely your rotation of 180 degrees rule, right? X, y becomes opposite x, opposite y. And you can do the same thing with y prime and k and z prime and L. So now this is where we're going to take our coordinates and rotate them by a rotation of 180 degrees. So now I'll do that here. I should do it in blue, right? Blue, blue. So in blue, when I rotate these 180 degrees, x prime is going to line up with j, and it's become -4, -2. -4, -2, which is accurate. Y prime is going to line up with k, and k is at -2, -8, which is opposite of 2, opposite of 8. And then L, which is z prime, is going to line up at -8, -2, which would be exactly the right idea. So your final answer here for this composition would be, okay, we did a rotation, rotations are lowercase, of 180 degrees about the origin, composed with a dilation, scale factor of 2, of triangle XYZ, sorry, skipping Y for some reason, XYZ, and it became triangle JKL. And there's your similarity transformation, right? Because it involves a dilation. Again, they did it the other way. They did the rotation first and then the dilation. Again, I don't think it matters. I just like to line up the points better. All right, so this is video 1. Video 2 is coming up soon.